In the previous lesson, we introduced the EPC and named its major components. You may have noticed a recurring theme. Some components handle signaling and others handle data. That division isn't accidental. It's one of the most important architectural decisions in LTE. By the end of this lesson, you'll understand exactly what the control plane and user plane are, why they're separated, and what the MME, SGW, and PGW each do within their respective planes. Every cellular network has two fundamental jobs to do. First, it needs to manage devices, authenticate them, track their location, set up and tear down sessions, and handle mobility. Second, it needs to move data. It needs to forward IP packets from the device to the internet and back. In older network architectures, these two jobs were sometimes intertwined in the same network elements. LTE deliberately separates them into two distinct planes. The control plane carries signaling messages, the management conversations that set up, maintain, and tear down connections. No user data travels on the control plane. It's purely about coordination and control. The user plane carries the actual payload, your sensor readings, GPS coordinates, firmware updates, or any other information your device sends or receives. The user plane is the data highway. This separation gives network operators and engineers three major advantages: independent scaling, resilience, and optimization. A network serving millions of IoT sensors that each send a few bytes per hour needs massive control plane capacity because there are lots of devices to manage, but relatively modest user plane capacity since there's not much data per device. Separating the planes lets operators scale each independently. If a user plane component has an issue, signaling can continue. Devices stay registered and trackable even if a function like data forwarding is temporarily interrupted. Likewise, if a control plane component has an issue, it's possible for existing sessions to continue passing data over the user plane. Each plane can also be optimized for its specific job. The control plane needs low latency for signaling. The user plane needs high throughput for data. Different optimization strategies apply. This separation is also the foundation for 5G's architecture, where the concept is continued with the CUPS, or Control and User Plane Separation framework. The mobility management entity is the central control plane node. Let's break down its four core responsibilities. When your IoT device first attaches to the network, the MME runs the EPS-AKA, Authentication and Key Agreement procedure. It retrieves authentication vectors from the HSS and challenges the device to prove its identity using cryptographic keys stored on the SIM. Once authenticated, the MME and device establish encryption and integrity protection keys for all subsequent communication. This ensures that no unauthorized device can use the network, and that signaling messages can't be tampered with in transit. After authentication, the MME orchestrates the creation of an EPS bearer, the logical tunnel that carries data between your device and the PGW. The MME tells the SGW and PGW to allocate resources, assigns quality of service parameters, and signals the eNode B to configure the radio bearer. This is the process that gives your device an IP address and a path to the internet. When a device moves from one cell to another, the MME coordinates the handover. It communicates with the source and target eNode Bs, instructs the SGW to reroute the data path, and updates the device's location in the network. For most IoT devices, especially stationary sensors, handovers are rare. But for asset trackers, fleet vehicles, and mobile devices, this function is critical. When an IoT device enters idle mode or power saving mode to conserve battery, it stops actively communicating with the network. If the network receives downlink data for that device, the MME initiates paging, sending a broadcast message across the device's last known tracking area, asking it to wake up and re-establish its connection. For IoT, the paging cycle is closely tied to EDRX configuration, which controls how often a sleeping device briefly listens for paging messages. While the MME handles all the control signaling, the SGW and PGW handle the actual movement of data packets. The SGW sits at the junction between the radio access network and the core network. Its primary role is as a routing and forwarding hub. Here's what it does. Local anchor for handovers. When a device moves between eNode Bs, the SGW maintains the data tunnel on the core network side. The eNode B changes, but the SGW stays the same, providing continuity for the session. Downlink data buffering. When a device is idle, the SGW buffers any incoming packets and notifies the MME to page the device. Once the device wakes up and reconnects, the SGW delivers the buffered data. The SGW records volume and flow information used for billing and, when legally required, lawful intercept. For IoT deployments, the SGW's buffering behavior is particularly important. If your cloud platform sends a command to a sleeping device, the SGW holds that command until the device's next wake cycle. Understanding this behavior helps you design appropriate wake-up intervals and avoid data loss. The PGDW is the edge of the cellular network, where the operator's domain ends and the public internet or private enterprise network begins. Its responsibilities include IP address allocation. The PGW assigns your device its IP address, either from a shared pool or a static assignment. For IoT, static IP addresses are valuable for devices that need to be directly addressable from cloud platforms. The PGW enforces quality of service, or QoS, policies on data flows, ensuring that high-priority traffic, like alarm signals, gets preferential treatment over routine telemetry. Working with the PCRF, Policy and Charging Rules function, the PGW applies data usage policies, rate limiting, traffic shaping, and billing rules. The PGW is where access point name, APN, configuration takes effect, which is a virtually and sometimes physically separate network space. A private APN routes your device's traffic through a dedicated isolated data path, a common security best practice for IoT fleets. Let's trace a complete device attach procedure to see both planes in action. Your device powers on and sends an attach request over the radio to the eNode B. The eNode B forwards the signaling message to the MME. The MME queries the HSS for authentication vectors. The MME authenticates the device and establishes security. The MME signals the SGW and PGW to create a default bearer. At this point, the control plane is orchestrating the user plane setup. The PGW assigns an IP address and returns it through the SGW to the MME. The MME sends an attach accept to the device through the eNode B, including the IP address. The data path is now established. Device to eNode B to SGW to PGW to the Internet, which functions as the user plane. Notice how all of steps 2, 7 are control plane operations, signaling that sets up the infrastructure. Only step 8 is the user plane actually carrying data. This device authentication flow is a sequence that begins at the RAN and passes through the MME and HSS before any user data can flow. The control plane and user plane are the two fundamental layers of LTE network architecture. The control plane, centered on the MME, handles signaling, authentication, session management, mobility, and paging. The user plane, built on the SGW and PGW, handles the actual forwarding of data packets from device to internet. Separating them enables independent scaling, resilience, and optimization. Understanding which plane a problem lives in and what clues can be found in each is one of the most useful diagnostic skills you can develop as a cellular IoT engineer.